In this video, we will be dealing with stoichiometry and then limiting reagent calculations, both of which are very important in chemistry. For our first example, if we were to react 52.9 grams of potassium chloride with excess red phosphorus, what mass of tetraphosphorus decaoxide would be produced according to the following reaction, where you have potassium chlorate reacting with phosphorus to make tetraphosphorus decaoxide and potassium chloride. So, where do we start? We start as we often start, and that is by balancing the reaction that is given. All right. So, this is the reaction that's given. We need to make sure we have it balanced. All right. On the left, I have 1 potassium. On the right, 1 potassium. On the left, 1 chlorine. On the right, 1 chlorine. On the left, 4 phosphoruses. On the right, 4 phosphoruses. But the problem is this now. I've got 3 oxygens on the left. I have 10 on the right. And I need now to figure out a common multiple between those. All right, the common multiple between 3 and 10. And the common multiple, of course, is 30. And so, in order to do this, I need 30 oxygens. Well, to get that, I need to put a 3 in front of the P4O10 and a 10 in front of the KClO3. So now that's balanced, but now I've got to go back and make sure everything else is balanced. Now I have 10 potassiums, which means I need a 10 in front of the KCl. I know it's hard to read, but that's a 10 KCl. And now I also notice what I have. I have 4 times 3, I have 12 phosphoruses, which means I need a 3 here in front of the P4 to make 12 phosphoruses. So now this is happily balanced. All right. So if you wanted to write down the actual fully balanced reaction, you'd have to say 10 KClO3 plus 3 P4 solids forms 3 P4O10 solid plus 10 KCl solid. So that then is my balanced chemical reaction. And now I can start the problem. And I start the problem by looking at what I'm given. I'm given that I have 52.9 grams of this material here, KClO3. I'm also told that I have an excess of red phosphorus, which is this species here. And by saying excess, what we're saying is we don't need to worry about it. We have plenty. We're definitely going to be able to run the reaction with P4. We don't have to worry about it. We can only focus on the KClO3. This will become important later in this video when we deal with limiting reagents. But for now, we don't need to worry about the P4. We can focus our attention on starting with the potassium chlorate. So, first we write down what we know. We have 52.9 grams of KClO3. And I can first convert that into moles. 1 mole KClO3. That has a mass. Now this is just the molar mass. So from the periodic table, potassium 39.10 plus chlorine 35.45 plus 3 oxygens, 3 times 16 gives me a number 122.55 grams. So that's converting from grams of KClO3 to moles of KClO3. Now, using my balanced reaction, I can convert from moles of KClO3 into moles of what I'm interested in, which is my tetraphosphorus decaoxide. All right, moles of P4O10. Using the coefficients from the balanced reaction, the number in front of the P4O10 is the number in front of the P4O10 in the balanced reaction, which is a 3. The number in front of KClO3 is the number in front of KClO3, which is a 10. So that's my second term. That's then converting from moles of KClO3, which I had coming out of the first term. That's canceling, and now I'm ending up with moles of P4O10. Okay, and now I can convert to what I want. I don't want moles of P4O10, I want grams, and I know 1 mole of P4O10 has a molar mass from the periodic table. I have 4 phosphoruses, 4 times 30.97, plus 10 oxygens, 10 times 16. Doing the math, this is 283.88 grams of P4O10. Now doing the math, 52.9 divided by 122.55 times 3 divided by 10 times 283.88 divided by 1, and I get a number which is the amount then of 36.8 grams of P4O10. And this then is the amount of tetraphosphorus decaoxide I should expect to be generating if I start off with 52.9 grams of potassium chlorate and excess red phosphorus, which is the answer to the first question. All right, moving along then. For our next example, what mass of iron 3 oxide and aluminum must be used to produce 15 grams of iron according to the reaction equation Fe2O3 solid plus aluminum solid goes to iron liquid plus Al2O3 solid. So what are we really doing in this case? What we're doing is they're telling you you have a known amount of this iron, and they want you to tell how much iron 3 oxide would I get from it, or I should say how much iron 3 oxide is needed to make it, how much aluminum is needed to make that amount also. So they really want to know how much iron 3 oxide and how much aluminum should I pour together to make that amount of iron liquid that they want. So how do we do this? All right, first off, just like before, we need to balance this reaction, because right now it's not balanced. I have 2 irons. I have 1 iron on the right, which means I need a 2 in front of the iron on the right. I have 1 aluminum on the left. I have 2 aluminums on the right, so I need 2 aluminums on the left. And now all the elements are balanced because I have 3 oxygens on the left, 3 oxygens on the right, 2 irons on the left, 2 irons on the right, 2 aluminums on the left, 2 aluminums on the right. Everything is happily balanced. Starting with the iron liquid that I know, I have 15.0 grams of iron. I can first convert that to moles, because 1 mole of iron, I know its molar mass from the periodic table is 55.85 grams. That gets me to moles of iron. And now I can go moles of iron into moles of what I want. Moles Fe2O3, let's say. And these numbers, remember, come from the balanced reaction. The number in front of the Fe2O3 is 1. The number in front of the Fe is 2. So 1 in front of the Fe2O3, 2 in front of the Fe. And then I can convert back, taking the 1 mole Fe2O3 using its molar mass to give me then grams. I've got 2 irons. Each iron is 55.85, so 2 times 55.85, plus I got 3 oxygens, 3 times 16, gives me 159.70 grams. And so, doing this math, 15 times 1 divided by 55.85 times 1 divided by 2 times 159.70 divided by 1 gives me 21.4 grams of Fe2O3. So that's how much Fe2O3, or iron 3 oxide, I would need to add. Now let's look at the aluminum, and we do the same thing again. We start in exactly the same place. 15.0 grams of iron. First convert to moles of iron. Just like before, 1 mole of iron is 55.85 grams. And now when I do my mole-to-mole conversion, I'm converting from moles of iron into moles of aluminum. From the balanced reaction, the number in front of Fe is 2. The number in front of Al is 2. And then I can convert 1 mole of aluminum, according to the molar mass on the periodic table, has 26.98 grams. And so I can figure that out. 15 times 1 divided by 55.85 times 2 divided by 2 times 26.98 divided by 1. So here I would then need, doing the math, 7.25 grams of aluminum. So I would need to mix together then, in order to get this reaction to work, 21.4 grams of iron 3 oxide and 7.25 grams of aluminum, and that then would guarantee that I make 15 grams of that iron then, which is the answer to the problem. Moving on to our next problem. What is the maximum mass of ammonia gas that can be produced from a mixture of 10 grams of nitrogen gas and 5 grams of hydrogen gas according to the reaction equation N2 gas plus H2 gas goes to NH3 gas? This particular problem is a limiting reagent problem. And I know that because I'm given an amount of each of the reactants, and I'm asked to find the maximum amount of a product I could make. But the first step, as has been the case previously, in the previous problems, is always determine the balanced reaction. Balance the thing. Right now it's not balanced. I have 2 nitrogens on the left, I have 1 on the right, so I need a 2 in front of the NH3. 2 nitrogens on the left, 2 nitrogens on the right. Now I have 2 hydrogens on the left and 6 hydrogens on the right, so I need a 3 in front of the H2 on the left to finish the balancing process. So now the reaction is balanced, and now I can turn my attention to doing the problem. What I'm going to do in this problem is convert from N2 into NH3, and then convert from H2 to NH3 to determine the limiting reagent. That's going to be the technique I'm going to use. So I'm going to start off with what I know first. 10.0 grams of nitrogen gas, N2. And I do exactly what I did before. Convert to moles. 1 mole, N2, weighs 28.02 grams. That's the molar mass of N2. And now from the balanced reaction, I can convert from moles of N2 into moles of NH3. The coefficient in front of NH3 is 2 from the balanced reaction. The coefficient in front of the N2 is 1 from the balanced reaction. And now I can convert 1 mole of NH3 is its molar mass, which I can figure out. I have 1 nitrogen, 14.01. I have 3 hydrogens, so plus 3 times 1.008. And I get a molar mass for the ammonia of 17.034 grams. So now I can do this math. 10 times 1 divided by 28.02 times 2 divided by 1 times 17.034 divided by 1 gives me 12.2 grams of NH3. So that's how, so basically now I'm saying if I have 10 grams of nitrogen and it all reacted, I could make 12.2 grams of NH3. So now let's look and see how much the hydrogen could make. Starting off the same way except with my hydrogen. 5.00 grams of H2. First convert to moles. 1 mole H2 has a mass of 2.016 grams. That's its molar mass. Convert from moles of H2 into moles of NH3. The coefficient in front of H2 is a 3. The coefficient in front of NH3 is a 2. And then convert 1 mole NH3 into grams, which we just did is 17.034 grams. I can do this math, so 5 times 1 divided by 2.016 times 2 divided by 3 times 17.034. Doing that, I find out that this amount of hydrogen could produce 28.2 grams of NH3. So what this is telling us, this is saying that if 10 grams of nitrogen totally reacted according to this reaction, it could make 12.2 grams of ammonia. If 5 grams of hydrogen totally reacted, it could make 28.2 grams of ammonia. Well, that means if I mix them, the most I could possibly make, therefore, is 12.2, because as soon as I make 12.2 grams of ammonia, I've run out of nitrogen. So this then is limiting. All right, so the nitrogen limited it, and this number is what we call the theoretical yield. Okay, moving on now to our final problem, which introduces another new concept into this problem, or into what we're doing. If 68.5 grams of carbon monoxide is reacted with 8.6 grams of hydrogen gas, and 35.7 grams of methanol is produced, according to the following reaction, what is the percent yield of the reaction? This is exactly the same as the last problem, with one additional change at the very end. As before, we always start by balancing our reaction. I have 2 H's on the left, I have 4 H's on the right, which means I need a 2 in front of the H2 on the left. So now I have 4 H2s, or 4 H's on the left, 4 H's on the right. 1 carbon on the left, 1 carbon on the right. 1 oxygen on the left, 1 oxygen on the right. By the way, that's H2 gas, not solid. Just notice that mistake. Okay, now that it's balanced, now we can do the problem. And we're going to start exactly the same way we've done before. We're going to take our known mass of carbon monoxide and convert to methanol, and our known mass of hydrogen gas and convert to methanol, and see which one produces less. So, starting off with 68.5 grams of CO. I'm going to convert that to moles. So 1 mole CO. From the periodic table, the mass of carbon is 12.01, and I have 1 of them, plus the mass of oxygen, 16 times 1. I do that math, and I find out the molar mass of CO is 28.01 grams. Now I convert moles of CO into moles of H2. Or sorry, not H2. Methanol, CH3OH. Mistake on my part. Using the coefficients from the balanced reaction, the coefficient in front of methanol is 1. The coefficient in front of CO in the balanced reaction is 1. And now I can convert from moles of methanol, so 1 mole of methanol, I can use its molar mass, which I can find from the periodic table. I have 1 carbon, so 1 times 12.01. I have 4 hydrogens, 4 times 16. I have 1 oxygen, 4 times 1.008 for hydrogen, and 1 times 16 for oxygen. Excuse me. So 32.042 grams. And doing this math, what do I find? 68.5 times 1 divided by 28.01 times 1 divided by 1 times 32.042 divided by 1. And it gives me that this could produce 78.4 grams of CH3OH. And so there, it's how. So if 68.5 grams of carbon monoxide entirely reacted according to this reaction, it could produce 78.4 grams of methanol. Now let's see about the hydrogen. So starting with my known hydrogen amount, 8.60 grams of H2. convert to moles. 1 mole H2 divided by the molar mass, 2.016 grams. So 2 times the mass of a hydrogen atom. Now I convert from moles of H2 to moles of methanol. Moles CH3OH. From the balanced reaction, the coefficient in front of methanol is 1, the coefficient in front of H2 is 2. And now I convert from moles of methanol, so 1 mole CH3OH, into grams, 32.042 grams of methanol. It's the molar mass of methanol again. So 8.6 times 1 divided by 2.016 times 1 divided by 2 times 32.042. And I get a number, 68.3 grams of methanol. So what's this telling me? This is telling me that in the event that 68.5 grams of carbon monoxide totally formed methanol, it could make 78.4 grams of methanol. If all of my 8.6 grams of hydrogen produced methanol, it could make 68.3. So the actual amount of methanol that I should be producing, as we did in the last slide, is the smaller of them, 68.3 grams. This is my theoretical yield now. To find percent yield, I use that. You see, I didn't actually produce that. I actually produced, not that, but I produced 35.7 grams, less than that. And that's pretty normal. So to find percent yield, so percent yield, you take the actual yield. How much methanol did we actually produce? Well, that's 35.7 grams. We divide it by the theoretical yield, which you just found, was to be 68.3 grams, and I multiply that by 100 to get the percent. So 35.7 divided by 68.3 times 100, and I find that this one, 52.3%. So this reaction, according to my math, and according to this problem, this reaction is 52.3%. So it produces its actual product in the real world, 52.3% of all the product that it could be producing ideally. And we never really get to the ideal case. We never get 100% yield, and you can never ever get more than 100% yield, but you can never really get to 100% yield, but sometimes you can come close.